Uh, okay, better be
I remembered
careful
that
what I
time.
say again. Now, if I can just find my pointer. I'm going to be talking about some data that indicate that, well, a lot of you are familiar with the winter ozone problem here in the Uinta Basin. Measurements, we have measurements going back now a little over 10 years. And for those of us who are following it closely, it probably has been obvious that the ozone concentrations have been declining over the decade. I mean, in the beginning part of the decade, we were seeing numbers around 120 and 140 ppb, and we haven't seen anything that high for the last few years. So this talk, I'm going to have two parts in my talk. I'm going to show a deep dive that we did into the data to try and demonstrate that that the decrease in ozone is real, and try and determine whether it's statistically significant or not. So that'll be the first part of my talk, looking at the data. The next part, I'm going to talk about why I'll get very speculative and talk about why we think the ozone might have decreased over the last decade. Obviously, that's good news that it's decreased, but on the other hand, the next question is, will it come back? And if we can't explain why it's decreased, then we also don't know whether or not it will come back. The purpose of this slide is just to show how we quantify inversion strength here in the basin in the absence of routine tetherson data. This plot on the lower right here just shows the elevation as you drive through the basin, along several of the highways. And all I'm trying to show is that if you look at the temperature along along those same highways on a cold day back in January 2013, that the temperature is well correlated with the elevation. That's an obvious indication of an inversion. It was really cold down here in the bottom of the basin and actually got warmer when we went all the way up to Daniel's Summit, almost all the way to Heber, or if we go up north in the direction of Flaming Gorge. So in other words, we can always expect surface temperatures also to be correlated with elevation, and we have lots of measurements of those. So we define something called the pseudolapse rate, which is just the variation of the surface temperature with elevation as you move about in the basin. And that's similar to the ordinary lapse rate, because that also involves the change in temperature with elevation. But I just want to point out that we're using surface temperatures. And whenever this quantity is negative, that indicates an inversion. And we calculate it each day. We have a number for that each day from a least squares line through the temperature elevation plots. On this slide, I'm just trying to show that there's a qualitative and a quantitative difference in the ozone phenomenon here, depending on whether or not there's snow on the ground. So in particular, ozone is consistently higher in seasons when we have snow and much lower when we don't. In fact, this more or less defines the wintertime background ozone of about 40 ppb. And the other thing I want to point out is that then there are 3 seasons in the past decade, 2012, 2015, and 2018, where we had low ozone. In the remaining 8 seasons, we had high ozone, because of course the snowpack plays an important role. So we have ozone concentrations now measured at 38 different sites over 11 winters, and so what I did is I generated scatter plots that show the ozone concentration as a function of this pseudolapse rate, or as a function of the intensity of the inversion. And in the interest of full disclosure, these two scatter plots are indicative of all of the others, except that they were cherry picked because they show very high correlations. But nevertheless, even when the correlations are weaker, they always follow this pattern, or almost always. In the absence of snow, we see positive correlation, like in this example, Roosevelt 2012. And when there is a snowpack present, there's a negative correlation, like in Ouray at 2014. This shouldn't be a surprise. I mean, we understand that because the inversions increase the intensity of the ozone, but this trend was, for me at least, was a surprise, and I think it's indicative that when snow is absent, then ozone is being removed by NOx. That in the presence of inversions and in the absence of snow, then the ozone is below background and is probably being titrated out by NOx. So, so once again, we see a positive correlation when there's no snow, negative correlation when there is. And the next thing I wanted to do, well, let's go to the next slide. I wanted to come up with a single number that characterizes the ozone intensity in any given site in any given season. So I took each one of these trend lines from all of the scatter plots and extrapolated or interpolated them to a pseudolapse rate of -15, which is a relatively intense inversion. And this is the name I've given to that extrapolation or interpolation. Just think of it as a measure of the ozone concentration at a given site in a given season when we've controlled for the strength of the inversion. This chart, okay, I don't expect you to read the table. One of the main reasons I put it up was to just indicate that for some sites, we have continuous readings over the entire decade. For other sites, we don't have, but nevertheless, for each site in which at each site where we had an ozone monitor operating, we're able to calculate one of these quantities. And then what I've done is I've taken each one of these columns, so all of the ozone numbers in any particular season, and I've gathered them into box whisker plots. Okay, so the blue diagrams are for seasons with snow. The red diagrams are for the 3 seasons without. And then the trend lines have been drawn using the medians from each one of these seasonal distributions. Well, as I said, there's good news. During snow years, the ozone has been decreasing. This line is statistically significant, and it decreases at a rate of about 3 parts per billion per season. By statistically significant, I mean the negative slope. The fact that it's sloping downward cannot be explained as just a random occurrence. For the no snow seasons, well, there are only 3 of those, and so it's harder to establish statistical significance, but the ozone during those seasons seems to be increasing. And the interesting thing is that both trend lines are converging towards background. And the fact that this trend line is positive, I think, is another indication probably that NOx is removing ozone when the snow is absent. Here's another plot that shows the same thing. So for each one of the seasons, I'm plotting the number of daily exceedances of the NAC standard of 70 parts per billion. And that's also over the snow seasons, that's also been showing a statistically significant decline. We now know we have in 2021, there were actually 2 exceedances. So the new point would be about this position here. This is also good news, but maybe we shouldn't be, I mean, to avoid to avoid non-attainment designations, we need to stay below the line here of 4 exceedances. So, so I guess we'll see what the future holds, whether or not we're able to stay below that limit. Anyhow, like I said, I'm ready at this point, at least, to speculate a little bit about the decline, what has caused it, and what we should be doing perhaps to try and prevent the ozone from coming back. First of all, there is evidence suggesting that the basin is under NOx control. There's some of you might be familiar with this box model, for example, and they showed a strong sensitivity to NOx in that model. There's an analysis that you can do. It also shows a strong sensitivity to NOx, but does not indicate, it doesn't let you calculate the sensitivity to VOC. So still there's another suggestion that it might be under NOx control. And the third is in the data that I'm showing here. These are VOC data, controlled for inversion strength, the same sort of construction as I prepared for the ozone. And so there's a steady trend line in NOx over the last decade, excluding these outliers, but they were taken at different sites, and so I think I'm justified in excluding these earlier years. So there's been a steady decline in NOx, but recently there have been upticks in VOC. We're not exactly sure why, and maybe it's not that robust because we only have data for two sites. But on the other hand, this at least suggests, because NOx and ozone have been decreasing, and the ozone didn't reflect this upturn in the VOC. So that's another suggestion that the system may be under NOx control. So let's ask the next question. If it is under NOx control, then maybe we can understand the decrease by looking for any significant declines in NOx sources. So these two pie charts come from the two UDAC emissions inventories for 2014 and 2017. RICE stands for reciprocating internal combustion engines. And those emissions, according to the estimate, declined by about 2,000 tons per year. And another decline we can see is in well completions. A well completion just refers to the overall process of going out and drilling a well and getting it ready to produce either oil or natural gas. So you can think of well completions or drilling. That's the activity of drilling, and those have also decreased. Most of these engines, turns out, are pump jacks. Those are those devices that you see that rock back and forth and pull the oil to the surface. And it does seem, well, according to information that we've received, more barrels of oil are being lifted in recent years by electricity than by internal combustion engines. So that may explain the decrease here of the 2,000 tons per year. The other thing that has decreased significantly since the early years are just the number of drilling rigs, and that correlates directly with well completions. A rig goes out, drills a well, and completes it. So well completions have also decreased. So that might be another part of the explanation. And finally, I'm showing the population of Uinta County over the last decade. It hit a peak in 2015 and then went through a 7% decline. That had to do with global, I guess more than anything, with the global price of natural gas, and the economy became more depressed. So during these years when ozone was high, there was also a lot of consumer confidence, people taking more trips just because the outlook was good. an economic boom, construction boom, lots of construction equipment coming into the basin and building. And then that was followed by a decline. My point is that the population is probably one indication that traffic-related NOx emissions have declined since the beginning of the decade. So finally,
5 minutes.
5 minutes. Okay, good. Finally, if there's if the basin really is under NOx control, and if the biggest piece of the pie are internal combustion engines, and most of those are pump jacks, then one suggestion for that we should be thinking about in order to solve the ozone problem would be to electrify the entire oil and gas field. So most of those pump jacks, like I said, are operated by engines because the electric grid doesn't go out there. This, of course, this doesn't say anything about the economics or the politics of extending the grid out there, but I, you know, at this point, I'm willing to make this conjecture that if we electrified the oil and gas field, we could offset NOx emissions that would occur when the economy rebounds. And that's everything I have prepared. Are there any questions?
We have time for questions. It looks like
I've got a couple.
Oh, go ahead, Randy.
Thanks, Mark. That was great. If first of all, you say you saw an uptick in VOCs, and from your graph, it looked like it was mostly, well, at least you showed ethane and benzene. Is that right?
And
then I was.
Well, this is TNMHC. So
yeah, TNMHC, but then down the other two below that. So ethane and benzene, is that right? Or toluene, sorry.
Toluene, yeah.
Toluene. So then on your other graph, you showed that the gas production has gone down, but the oil production has gone up in about those same years, 2000, yeah, they're 16 and so.
Yeah, oil production has remained pretty much steady, although gas production has declined.
Well, oil production peaked out, then dropped, and it's going back up again.
Yeah,
so
yeah.
do you relate that with particularly the ethane, the lower molecular weight hydrocarbons being from those oil productions, or just we don't know? So I guess why is the hydrocarbons kicking up? And then that kind of leads me to what your conjecture was: if they electrify the oil and gas fields, and then relative NOx availability goes down, would it then maybe switch back to a VOC limited regime? Would there be enough?
Yeah, that's always the question, isn't it? If you turn one down, then you may switch into the other regime, and yeah, I don't have any idea. I mean, at this point, it's probably important to control both NOx and VOC. And by the way, we've wondered what this uptick is, what is responsible for that, and we're not sure.
Roosevelt, yeah. Huh. Well, that's interesting. Still got good work to do out there then.
Yeah.
Thank you.
Mark, thanks. Rachel has a question in the chat. She's wondering about the number of days per year that meet the pseudo-lapse rate criteria and how you grouped into snow and non-snow years. I think are there some days with a very low pseudo-lapse rate, so strongly inverted, that don't have snow, for example?
Well, one part of the question, I just used this diagram essentially to define the difference between seasons with snow and without snow. We may have one that's intermediate, but at least for the last decade, the snow depth has been very minimal. See, this is around 1 centimeter, and that's really not enough to produce the ozone. So I hope that answers your question. That's how we're distinguishing between one, the snow depth is very low, and two, the ozone is obviously following a different trend than in the seasons that were with snow. And while at the same time, the average snow depth, this is averaged at different sites across the basin. The average snow depth was anywhere between 8 centimeters to about 24 centimeters. And let's see, what was the other question?
I think that more or less answers it, as far as I can tell from the chat.
Okay.
Okay.
Oh, there was a question about inversion intensity when there's no snow, right? So yeah, you can have inversions. That's just that the snow intensifies them. I'm not a meteorologist, but under high pressure systems, we can have it. Inversions are typically weaker without snow, and you can see that on this slide. So we had looks like about a -8 here, whereas it got down below -20 here in this season. So.
Okay, great. Thanks, Mark. And thanks to everybody.